Good morning. I welcome you back for this second day of this 2 days online workshop on computer-aided engineering analysis using HyperMesh and Deform 3D. So today we are going in the morning session. We are going to see some of the basics and introduction about the machining process simulations. What are the basic things that we are going to consider? What is a finite element analysis and how it is integrated with the machining process. And in the afternoon session, we'll be having some hands-on training using Deform 3D software. So turning process will be simulated using that software in both two-dimensional and three-dimensional manner, so that we can interpret the outcomes of that simulation. So the morning simulation, the morning session, we are going to see the finite element analysis in machining process. What makes us to simulate or analyze the machining process? The first thing is we should know how a system behaves. So this finite element simulation of machining process is used to know how a machining process behaves with varying the input conditions. And second, to approximate. So we have to be very, very careful with this word approximate. Right? To approximate a nearby solution with that of the experimental work. So we cannot really have a reading or an output near to that of the experimental work, but an approximation can be done by using this finite element analysis. And the third one is it is economical. The simulation studies are more economical than the laborious and cost-oriented experimental works. For example, I am going to study the effect of machining parameters. So everybody knows what is machining parameters is. That is cutting speed, feed rate, and depth of cut. I am having 10 values in cutting speed. So in order to study the influence of cutting speed, I have to carry out 10 different experiments. And from that only I can determine how this cutting speed influences the outputs. The outputs may be a tool wear, or it may be cutting force, or it may be the surface integrity, anything. So how this cutting speed is going to influence that? So for this we require a experimental setup, a CNC machine or a ordinary central lathe. Then we require a workpiece material. Then we require a cutting tool. Then some persons to carry out that. So this makes it a economically feasible thing. So simulation studies eliminate all these things so that the economical aspects of this machining process will be reduced. But it will produce only an approximate result. So that we have to bear it in mind. So here we have many software packages to carry out the simulation process. We have Abacus, we have Deform 3D, Deform stands for deformation. Then we have ANSYS. ANSYS also we can incorporate this machining studies. And Advantage, we have another software that is called as Advantage. Both the two-dimensional and three-dimensional manners, we can do this machining process simulation. The difference between the software packages that is specific for machining process simulation, such as Deform 3D and Advantage, how it differs from the ANSYS and Abacus. So these two softwares, Deform 3D and Advantage, have user-friendly graphical user interface. It is very, very user-friendly, but in the case of ANSYS and Abacus, we have to model accordingly. But when compared to that of Abacus and ANSYS, these two are very, very user friendly. So with this, we move on to the introduction section of this presentation. So this simulation studies also falls under the computer aided engineering. So what is meant by computer aided engineering? Computer aided. So we are going to use computers to perform some engineering task. The engineering task may be analysis, analysis of a beam, an analysis of a component, analysis of a automobile body, analysis of a chassis, or in our case, analysis of a machining process. So here in this case, we are going to use some computers to perform some engineering task, and that is the CAE, computer aided engineering. But in the broad classification, the CAE can be categorized into finite element analysis, that is FEA, then computational fluid dynamics, CFD, and then multibody dynamics. The finite element analysis is the simulation studies of machining process, the analysis of beams, analysis of a component, likewise. In the CFD analysis, a heat transfer analysis, a CFD, a heat transfer analysis, how a turbine blade works, how a fluid gets transported, how a heat will be transferred through a fluid. And then multi-body dynamics, everybody knows it's the behavior of the, for example, a car, a crash analysis, likewise. Now we are most focused on this FEA, the finite element analysis. So in this finite element analysis, we have this finite element method. We have this finite element method, which is nothing but a numerical technique. The finite element method is a numerical technique that is used to perform the analysis. Why we are going to call it as finite element? Because the design space or the domain will be segregated or discretized into small element, finite elements. Since we are going to break the total component into small elements, we are going to call it as a finite element. What we are going to discretize? The physical phenomena. A component is the physical phenomena. In the case of machining simulation studies, it is nothing but the workpiece and the tool. It is nothing but the workpiece and the tool. So that we have to discretize. Okay. So what actually we are going to do in the finite element analysis? So in this, we are going to describe the process by means of some partial differential equations. So here nothing but we are going to create models based on the partial differential equations. So that's why we call it as a numerical technique. Then before entering, we should be very specific about what is meant by model and what is meant by simulation. So a model is nothing but a definition of a system that is equivalent to a real process or a system. A real process is there. For example, take it a turning process. The real turning process is made as a model. So a model is nothing but a realistic experimental one. But it has the same properties and characteristics of the machining process. The characteristics are, we have a material for the workpiece. We have a material for the tool. We know how it is going to be interconnected. What are the properties that both will have? The tool should be rigid. The tool should be rigid. It has some geometrical factors. For example, a relief angle, a nose radius, a rectangle. So likewise, it has some creep properties. So that should be included into the realistic model. Then only the real system will be converted into a model. So we should incorporate all the key properties and characteristics into the model. So for what purpose we are going to develop this model? A model is nothing but the resemblance of a realistic process or a system. So for what purpose we have to develop this model? So it is particularly useful for investigations, for experimental investigations, for calculations. So what is this calculation? So in real-time models of a turning process or a drilling process or a milling process, we'll come across the cutting forces, measurement of cutting forces. So that cutting forces can also be predicted by using these models. So it is used for investigation of how a process behaves, and we are going to calculate the outputs. For example, the cutting forces, the temperatures, because whenever a cutting tool comes in contact with the workpiece, at the interface the temperature rises up. So that interface temperature can also be calculated by these models. And more specifically, these simulation studies are used to in demonstration purposes. What is meant by a turning process? What is meant by a drilling process? How the chip will be produced? How the cutting tool will come in contact with the workpiece? So for these kinds of demonstration purposes, the simulations can be carried out. If I am going to carry out this in the real-time experimental investigation, then obviously more amount has to be spent. That is, the experimental works will be more expensive, and it is not possible for everyone to demonstrate. So for this purpose, we are going for this finite element simulation studies by developing an appropriate model. So what a model actually consists of? It consists of some general statements about the element type. So everybody knows in finite element there are different element shapes. Okay, what are the different elements that it has? The structure of that elements and how it behaves as a section of the reality. So in real-time conditions, in an experimental process, how the system behaves. The similar system is being incorporated in the finite element simulation models also. And the final thing is simulation. So far what you have seen is about the model. A model is nothing but an equivalent to a realistic system which is used for demonstration purposes and for calculations, and it has some general statements about the element structures and behavior. After developing the model, we have to simulate. After developing the model, we have to simulate. Then only we can see the outputs or the system, how it behaves. So the simulation is nothing but the imitation of a dynamic process of a model. Okay, so what we are going to obtain from the simulation studies? We are going to obtain knowledge, how a turning process behaves, how a drilling process behaves. So if I am going to choose this workpiece material, then what will be the chip that will be produced? If I am going to provide this much amount of cutting speed, this much amount of feed rate, and this much amount of depth of cut, what will be the chip condition? Because chip morphology is an extensive study. Chip morphology is an extensive study. Okay, so the simulation is nothing but the imitation of a dynamic process. So from this we are going to acquire some knowledge that can be transferred to the realistic conditions. So in the starting itself I have told these simulation results will be an approximate to the realistic one. So we'll have some knowledge, gain some knowledge from the simulation studies, and then we can apply it to the realistic work. So what is the need for a machining model? So the outputs of any machining process, whether it is turning, drilling, milling, boring, or whatever it may be, So the important parameters that will be interested will be on the cutting forces that is developed. So cutting forces, if it is higher, it will weaken the tool. So it will chip it out or it will break. And the temperature. The temperature is the interface temperature we are more concerned about. If the interface temperature is higher, obviously the tool will get softened out. And also the machined surface will have a different microstructure. So microstructural changes will happen because of high interface temperatures. So we are also more concerned about the interface temperatures. Then the chip morphology, whether it is a segmented chip, whether it is a continuous chips, whether it is a discontinuous chips or segregated chips, or it with built up edges. It all depends upon the input conditions and also based on the workpiece material. If I'm going to consider a brittle material like cast iron, then obviously we will be ending up with the segmented chips. If I'm going to consider copper, then long curved continuous chips will be produced. And also it also depends upon the machining parameters, cutting speed, feed rate and depth of cut. And apart from them, we have the principal stresses. So what is the maximum principal stresses that we will have during the machining process simulation? That can also be calculated. And what are the strains? Because materials will be removed by pure shearing action along the shear plane. In turning model, we'll consider a shear plane. So the material will be sheared along that plane and the unwanted material will be removed as a chip. So we are more concerned about the stresses and strains, which we can calculate prior to a experimental work. So in experimental works, we are not able to determine all these things in detail, but by using an appropriate finite element model developed, we can determine these things. So with this knowledge, we can do the experimental work. So we are going to gain knowledge from this machining simulation studies, and then we are going to apply that knowledge to the realistic condition. So consider a experimental work. So as told, I am going to take 10 cutting speeds, 10 feed rate, 10 depth of cuts to study their influences. So I have to carry out 30 experiments, which is a laborious work, which involves lots and lots of manpower, energy, work pieces, and all these things, utilization of machines, everything. So it is a more laborious work and also it is costlier because we have to use cutting tools, we have to use coolants, we have to use workpieces, the energy is the power that is required to run the lathe. And also look at the time that it consumes. It consumes higher amount of time. The simulation also consumes larger time periods, but economically it is good than that of the experimental works. So in the experimental works, if it is a trial and error approach or experimenting by means of trial and error, the obviously this finite element simulation studies will be a boost to your work, so that we can understand while changing the cutting speed, what is the effect on cutting forces, what type of chip will be produced, and what will be the change in interface temperatures. That we can determine. So with modeling, with an appropriate model of the realistic machining process, the resources are spanned. We are not going to use any resources. So we are going to preserve these resources, and apart from them, the very much important thing is optimization can be achieved with less cost. What is optimization? So it's a very big topic. So optimization is getting the best out of the available resources. I have a limited resources. From that limited resources, I am going to get the best. I am going to get the best out of that. So with this appropriate model, so I'm using this word appropriate because many models can be built. Only a perfect model will produce a nearby solution. That's why an appropriate model will achieve a good optimized condition with less cost. So what are the benefits of modeling the machining process, or what are the benefits of a machining model? So it reduces the experimental work considerably. Since it is a simulation studies, we can have it in our system itself, that is by using a computers, because the computers are the superpowers. Okay, with the higher processors, it makes us very easier. So this modeling reduces the experimental work considerably. And also the fundamental issues that relates to any machining, right? The fundamental issues of many machining practice should be understood in depth. Without that understanding, we cannot straight away go into the experimental work. So in order to learn the fundamentals of machining theories, these kinds of models and simulation studies are very essential. So the most important thing is it forms a feedback loop that is vital for machining simulation. Because if I want to do some research in a machining process, for example, a turning process or a drilling process, I should know the basics that is involved in the machining process. So by doing the simulation studies, I am aware of the basics that involves in the machining process, so that I will be using it in the experimental conditions. So it forms a feedback loop, that is a closed loop system. So I can understand the basics that relies on this machining process. So that knowledge I am going to use it in the experimental setup. Because when I understand the basic fundamental concepts in a better way, it is the best next thing to the ability of production. If I understand the basics well, or if I am sound enough in the basics, then obviously my knowledge in that machining process will be high. So I can predict if the cutting speed increases, what will happen to the chip, what will happen to the cutting forces, what will happen to the tool wear, what will happen to the interface temperatures. So with the prior knowledge, I can tell these things. So I can predict things with a better understanding. So what are the drawbacks? So if I have any advantages in system, then obviously there will be some limitations also. But here in the case of a machining model, rather than calling it as a drawback, we call it as the difficulties. We call it as the difficulties. So rather than drawbacks, these simulation models have some difficulties. So it doesn't have any drawback at all. The machining simulation models does not have any drawbacks at all, but it is the difficulties that we experience during the model development and simulation studies. So what are the difficulties that we are going to have? So during model development, there will be many variables that may be taken into account, but I cannot consider all the variables because of some aspects. For example, if I am going to consider a turning process, not only the machining parameters I should consider, like machining, cutting speed, feed rate, and depth of cut. Apart from this, we have the type of cutting fluid. How I am going to supply the cutting fluid? That is also a major one. Then, what type of cutting tool that I will be using? Whether I am going to use a high-speed steel or a carbide tool. In the carbide also, whether it is uncoated or coated, or ceramic tools, or diamond tools, or PCD, polycrystalline diamonds. Likewise, there are many tools that we can use. Whether I am going to use a high speed steel or a carbide tool, in the carbide also, whether it is uncoated or coated or ceramic tools or PCD, polycrystalline diamonds. Likewise, likewise, there are many tools that we can use. And apart from that, we have some geometries of tool. For example, the rectangle, the relief angle, this nose radius, then approach angle. Okay, so similarly, we have many aspects, but during simulation studies, we cannot consider all this process, because whenever you are going to consider this, then the system will become more complex. So there are too many variables that need to be taken into account, but we will not consider that. So that is one of the difficulties. So there are a lot of machining operations that are similar. For example, turning uses a single point cutting tool. Milling uses a multi-point cutting tool, and drilling uses multi-point cutting tool. Similarly, grinding. So these are all have similarities. These are all, even though it looks similar, but they are not similar, because there is a difference between using a single point cutting tool and a multi-point cutting tool. Okay, so even though it looks like similar, it is not similar. But we are going to consider only a universal model. So for all this process, we are going to consider only a universal model and not a realistic model. So actually, turning there should be a different model, milling there should be a different model, for drilling it should be a different model. But since some similarities exist, even though it is not similar, with some similarities, we are going to develop a universal model. So that is not a realistic one. So that is the difficulty that we will be facing. So in turning process or any machining process, we generally come across the orthogonal cutting system. So there are two types of systems. One is oblique and the other one is orthogonal. So we will be adopting only the orthogonal cutting systems, and we will have these shear plane models. So and we will consider only the shear plane models, that is the plane at which the shearing action takes place, so that the material will be removed as chip. So these two models only we will be normally considering, but these two models are under criticism. Okay, because this orthogonal machine cutting system is easy to adapt, whereas the oblique is a little bit complex in nature. So we are going to adapt the easiest one. So that is a criticism that we will be having. Next, the machining. Even though we call it as a general machining process, the fundamentals or the basics that relies on the machining operation is least understood. So what is the mechanics of metal removal? So all these things, it is least understood. So that is another difficulties that we will be facing in this modeling process. So during machining, the cutting tool will come in contact with the workpiece at a small region. The contact will be at a small region, but the stresses and strains at the small region will be very, very high, right? So this machining process involves very large stresses and strains in a small volume at a high speeds, because you can see the speed of the workpiece that rotates will be higher. So that is very, very difficult to model in a realistic condition. So that is the another difficulty that we will be facing. And the next thing is the complexity in the mechanism of chip formations. So the chip formation study is also an important study. Okay. Whenever we are going to consider this chip morphology, chip formation studies, then it leads to complex system or complex theories. Normally, we will be having this Pispanian model of chip forming. In chip formation, we will be considering this Pispanian model. So that we will see in the subsequent slides. So which is nothing but a stack of cards. It is nothing but a stack of cards. That is, layer by layer, the metal will be removed. So the mechanism of chip formation is complex. That leads to a complex theories. So if I'm going to develop a model based on this complex theory, then my model will also be a complex one. But whenever we develop some model, we assume some things. Whenever it has some complex things, that we will assume it as a constant. That is, we are going to make an easier way to model a realistic process or a system. See, models always include simplifications, but the oversimplification is lacking. That is, they cannot determine the outputs, a perfect outputs from the simplified models. From the simplified models, we cannot determine the appropriate nearby results. So if I am going to consider that complexity in my model, then it will be, the results will be nearby to the experimental results, but I am going to make simplicity in my model by some assumptions. So that makes my model a under evaluated model. Okay. So because of this, the result will be inaccurate or error. So there will be error in my results and it will be inaccurate. That's why we use these words approximate results, because we are going to develop a model with some assumptions. In realistic words, there is no assumptions at all. Since we are going to assume some things, the results that is obtained from the simulation studies will be either inaccurate or errors. Apart from this, the variation of tool and workpiece properties and geometric characteristics, the machining conditions, and the usage of cutting fluids. The cutting fluids may be provided as a cryogenic cutting fluid, liquid nitrogens or carbon dioxide that we can provide, or flood cooling I can supply, or dry machining we can do, or minimum quantity of lubrication, we call it as MQL. So there are many aspects of supplying the coolants in the interface of cutting tool and workpiece. So apart from this, the variation in tool properties, the workpiece, because there will be a variation within the workpiece. For example, if I am going to consider a composite material that is reinforced with some ceramic particles, what happens when the cutting tool comes in contact with the matrix material, or if the cutting tool will come in contact with the reinforced material? If the cutting tool comes in contact with the matrix material, it removes the material easily. But when the cutting tool comes in contact with the reinforcing materials such as ceramics, silicon carbide, Al2O3, boron nitride, then the wear on the cutting tool will be higher. So in that case, so more stresses or higher cutting forces will be developed. So these are some of the variations that exist in the realistic models. So if I'm going to consider all these in this model, then the complexity of the model will be higher. But we want a simplified model. With a simplified model, only approximate results can be obtained. If I want a nearby results, then I have to improve, or I have to accept the complexity of the model. So what are the things that is needed to develop a model? So the selection of process is the first one. Whether we are going to model a machining process, whether it is a turning, drilling, milling, boring, or sheet metal, or forming process, or rolling process. So first we have to select the process. Then we have to select the appropriate material for tool and die. So tool, whether I am going with the HSS or I am going with the tungsten carbide or I am going with the ceramics or cermets or stellites. Then determining the cutting conditions. What is the cutting speed that I am going to use? What is the feed rate that I am going to use? What is the depth of cut that I am going to use? It all depends upon the type of model that I am going to select. So different model consider different materials, models, different flow stress models, different thermal models. So these different types of models that we'll be using, we'll see in the next subsequent slides. So for friction, there will be separate model. For flow stress, there will be separate model. For tool wear calculations, there will be another model. For calculating the temperature, there will be another model. By selecting these appropriate models, we can develop a better realistic model. Then after selecting an appropriate model, the things that we consider is the meshing, because after developing a model, I have to discretize. Discretization is nothing but dividing the entire domain into small elements. Then that elements will be interconnected by means of nodes. Okay, so that we have to mesh, interconnect, and then we have to apply the boundary conditions. Then we have to apply the boundary conditions, and then the chip separation criteria, how the chip will be separated out, right? That also it should include. So by incorporating all these things only, a better model can be built. So what type of element that we are going to select, how we are going to meshing, that is interconnected, what are the boundary conditions that we are going to apply, so what are the formulations, so that is what are the models that we will be using for temperature calculation, for cutting force calculation, for friction calculations, for the flow stress calculations, what are the models that we will be adapting, and how the chip will be separated out from the workpiece. So our model should include all these things. So we cannot answer a question, this kind of questions, once an appropriate model is selected. Okay, there are many models. Johnson-Cook's is there, Oxley model is there. Okay, there are machining models are there. So what particular type of model that we are going to select for the simulations? Okay, this Oxley method, this Johnson-Cook and all these things we can see later on, and also during our hands-on training. Okay, so adapting different models produces different results. Adopting different models produces different results. Then how to select a model? A model should be selected based on the output that we require. For example, if I want to determine a cutting force, for cutting force which is the appropriate model, so that a nearby results may be obtained. So this model selected should provide a reliable answer to the output, that what we are going to look for, based on the input conditions that we are going to provide. So in modeling techniques, there are 5 different models we will be coming across. The first one is the empirical model, second one is the analytical model, third one is the mechanistic model, fourth one is the numerical model, and then artificial intelligence modeling. So each and every technique of model is different from one another. So what this empirical model actually means? So empirical models are developed based on the outcomes of an experiment. For example, I am going to perform 20 experiments in a lathe, that is a turning operation. So based on the outputs, the inputs considered will be cutting speed, feed rate and depth of cut. And the output that I am going to obtain is cutting force and tool wear. So 3 inputs and 2 outputs. So 20 experiments I am going to carry out for different combinations of input parameters, and the corresponding outputs are measured. So now I have 20 set of experiment reading. Based on that, I am going to develop a model, and that is the empirical model. So these empirical models can be developed by means of regression analysis. By means of regression analysis, we can develop a model. Okay. Then comes the analytical model. So these analytical models are based on mathematical models. Vt power n is equal to c. Vt power n is equal to c. Surface finish Ra is equal to nose radius divided by 32, R divided by 32. So these are all mathematical models. So if I want to develop a model from the previously generated mathematical models, then it is called as an analytical model. So analytical models are purely based on mathematical models that are developed by previous researchers and scientists that produces a better results, and that is proved. Okay. Then we have the mechanistic models, a mechanism. So mechanistic is nothing but a mechanism. So working of the individual parts that we are going to examine first. So how individual parts work, right? Then I am going to couple them. So that a mechanism can be developed. A mechanism can be developed. For example, the working mechanism of a robot that I am going to provide by means of a model. Then it becomes a mechanistic model because the robot is working is based on some mechanisms. So that is mechanistic model. Then we have numerical models. So analytical and numerical. Analytical is the model that is developed from mathematical models, equations. So in numericals, we are going to combine large number of mathematical equations. So that is the partial derivative equations and difference equations likewise. Okay, so large number of mathematical equations we are going to combine. By combining, we are going to have an approximate solution. So this word approximate we'll use whenever, because whatever results that we are going to have from the simulation studies is only approximate. So a nearby or a perfect prediction with that of the experiment results is not possible. Now presently I am going to simulate one turning process. I will have some result. The same input conditions, the same material, the same model developed. If I am going to run after 2 days, that will produce different results. But it will be nearby. That is not a problem. But only approximate results can be produced and the exact results cannot be produced. And the fifth one is the artificial intelligence model. That is the artificial neural networks, the fuzzy logics and all these things. So which have some linear functions and activation functions. The other name for activation function is the transfer functions. Sigmoidal function, ramp function, step functions that considers some weightages and bias. So the fifth one you can understand only when you know the ANN process, the artificial intelligence process. So apart from them, it is based on the experimental work from some mathematical equations, from the mechanisms. The model that is developed from mechanism is mechanistic, and if I consider larger number of mathematical equations, then it becomes the numerical one. So more complex model requires more input data, because the more complex your model is, the computational time will be higher. Even it will run for 2 days. So you know some components of an engine or an aerospace engine will be fed into a master computer so that it runs for days. And finally we will have a solution. So these simulation studies will run for hours or for days so that the outputs can be obtained. So the computational time increases with the complexity in the developed model. But in developing a complex model, we should consider more number of input data. Right? So the complex model, even though it takes computational time or higher computational time, the results that will be produced will be more accurate and it will be a nearby results. In the early days of simulations, so when the simulation was first introduced, the utmost important is the toolware only, because the quality of workpiece that is produced and the rate of production, everything depends upon the toolware. In economic aspects also, if a tool wears rapidly, then more number of cutting tools should be used, because after some time period we have to replace the worn out tool or a blunt tool. But from tool wear, now with the sophisticated facilities that we have, apart from tool wear, we are also showing interest. We are also showing interest in determining the cutting forces, the interface temperatures, the chip morphologies, okay, then the pressure that is being applied, and what is the surface finish that is produced, what is the change in microstructure at the machined surface that we can determine. Okay, so there are many things that we can study nowadays with the sophisticated models. But with sophisticated models, the complexity increases. But we can produce or we can predict more number of outputs. So here comes the high-speed machining. So machining at a higher speeds, higher cutting speeds is high-speed machining. Then there is another word that is called as hard machining. HARD, hard machining. Machining hard workpieces. It is a replacement for grinding actually. The hard machining is a replacement for grinding. Then we comes on hot machining, HOT, hot machining, that is machining the heated workpieces so that higher material will be removed with less stress, less cutting force, with lower tool wear. So that also we are researchers. So researchers are doing works on this hot turning, hard turning, then comes the cryogenic machining. So many works are being carried out nowadays. And apart from this high-speed machining, the researchers and scientists are also working on environment consciousness, that is limiting the usage of cutting fluids. So initially they targeted only the tool wear. Afterwards they came for the accuracy, then cutting force prediction, then interface temperature prediction, then what type of chip is being produced, then they comes for high speed machining, then they are environmentally conscious, that is how we are going to supply the coolants, because at the high temperatures, interface temperatures, when I supply the cutting fluids, it tends to evaporate because it takes away the heat. So heat dissipation is the important thing in machining. So for this purpose only we are going to provide the cutting fluids. So these cutting fluids, when supplied into the interface temperature, they tend to evaporate. If the operator inhales that, then it will be a health hazard. And also the recycling of these cutting fluids, okay, the processing of these fluids is a very basic task. That's why they are going with dry machining. In the dry machining, we don't use cutting fluids. But we use cutting tools that are extremely hard, like polycrystalline diamonds, cermets, likewise. Okay. So cutting fluids may be flood cooling. So we have to open. So that flood type cooling or dry, that is no cutting fluid. And apart from this, we are going to supply cryogenic materials at low temperatures, liquid nitrogen. carbon dioxide. So these are all called as cryogenic machining. Then comes the mist cooling or MQL cooling. That is minimum quantity lubrication, that we spray mist as a mist will spray with some external pressure. So air will be blown, in that droplets of fluids, cutting fluids will be made to pass, so it becomes a mist cooling. Right? So the outputs can also be improved by this. The purpose is to eliminate the cutting fluids and the hazards that is related with the cutting fluids. So this is the evaluation in machining process. So that should also be included in my developed model. So these analytical models, the analytical models uses mathematical equations, that is partial differential equations that it will be using. So these are used to predict, these analytical models predicts the cutting forces through some equations. So that the equations will have some constants. The hardness of the material, the strain hardening. Okay, so there are many constants that will be taken care of. Okay, so even though we are going to consider some constants based on the material that we are going to select, it will be totally different from the realistic work. So selecting an appropriate model is very, very essential. So nowadays, these FEM models are coupled with thermomechanical analysis, that is thermal as well as mechanical. So the cutting pressure, the cutting temperature, the stresses, cutting forces, the tool wear. So everything is coupled with the finite element models. By incorporating these things, the complexity of the model gets higher. With the higher complexity, the computational power required will be higher. Okay, at the same time, the computational time will also tends to increase. So that is the one of the drawbacks of this finite element studies. But in the case of artificial intelligence techniques, these are all really fast. This predicts better results, right? But they focus on a particular parameter. So what is my input? For that only a model will be developed, and it focuses on the particular output only. It won't provide the other outputs. So it gets focused on a parameter or a specific area. Then I have developed a model. In some cases, my model will fail. So what are the possible reasons for that? A model fails when it cannot predict accurately. When accurate prediction is not possible, obviously the models will fail. So models fails when it is not fast enough or when it is not simple. I am going to consider a complex model which I don't understand. If I am not understanding the developed model, then I lack knowledge, lacks the level of knowledge. So the model that I selected tends to fail. Okay, and if it's not fast enough to converge my results, then it is a waste. If it runs for 10 days, if it runs for 1 month, then the computational time is really, really high. So my model lacks the convergence. So it is a waste model, or the model tends to fail. So the reasons because of which this model fail are lack of accurate input data, right? Inadequate inclusion of all important parameters. So normally during analysis we consider only the main parameters. In turning, cutting speed, feed rate, depth of cut. This we call it as the machining parameters. Normally we will be considering only this. But apart from this, we should also consider the tool material that we are going to select. Whether I am going to consider coating or uncoated tool, then what is the nose radius, what is the approach angle, what is the relief angle, Okay, so there are many parameters that is associated with turning process, but we are not going to include all these things. So that is inadequate inclusion of all important parameters and misuse of a modeling technique, not selecting appropriate models. So that also leads to failure of a model. Now, what is the finite element analysis? So this finite element analysis comes into play because of the higher computational power that is available in the present decade because of the revolution in the computer technology. Because based on the computational power that these computers have, we have n numbers of computational techniques that are developed to solve engineering problems. So for this analysis, this mathematical modeling, that is analytical as well as numerical techniques, forms the integral part. So for numerical methods, we consider 4 different types. One is finite difference method, the next one is the finite element method, then finite volume method, and then boundary element methods. So different methods will be selecting upon. So now what is the finite difference method? So the finite difference method, so everything will be using some partial differential equations. In simulation studies, we will be using partial differential equations. So how we are going to deal with that? So that makes the difference. In the finite difference method, we are going to solve these differential equations by approximating them with the difference between the derivatives. So solving the differential equations by approximating them with the difference in which finite differences approximate the derivatives. So what is the difference between these differential equations? That we are going to approximate, and then we are going to determine the outputs. Then comes the finite element method. So these are also numerical methods. These numerical methods are going to use numerous mathematical equations. So if I am going to use a mathematical equation, then it becomes analytical. If I am going to consider more number of mathematical equations, then it becomes numerical. So these finite element simulations uses only numerical methods. That is, it considers more than one mathematical equations in forming the model. So this finite element method is governed by elliptical partial differential equations. Right? Elliptical partial differential equations, and these are also called as boundary value problems, because here in this study we are going to provide the boundary conditions. That is the design space or the domain. We call it as the domain. So within the domain only, the component boundaries only, it is going to develop a feasible solution. Then comes the finite volume method. Right? So it represents and evaluates these partial differential equations by means of algebraic equations. It is purely based on volume. That's why we call it as a finite volume method. The flux entering a given volume is identical to the leaving the adjacent volume. Right? The flux entering into a given volume, that is into an element, is identical to the flux leaving the adjacent volume. Since it is based on the volume, okay, it is called as finite volume methods, and this also uses the partial differential equations. Then we have the boundary element method. So this boundary element method is specifically used in CFDs, computational fluid dynamics. Okay, so this also uses linear partial differential equation. So here you can see all these methods are using only partial differential equations, right? So these partial differential equations in boundary element method is formulated as integral equations. Okay, so that includes the fracture mechanisms, the fluid mechanics, and contact mechanics. Okay. So why we are going to consider FEM, the finite element method? So it is the most flexible. These methods are most flexible and are versatile in nature. Okay, it's most flexible and versatile. For what purpose? For solving some engineering problems. So this FEM is made up of or built up of many small interconnected subregions or elements. That is, I am going to consider a domain, okay, or a component or a part that I am going to divide it into single elements or simple elements, that is called as finite elements. That is called as finite elements. So each and every element will provide a piecewise approximation. That is a solution. The piecewise approximation is a solution for an individual elements. So by combining all these solutions, I am going to provide the solutions for the total domain. So this is the procedure of finite element methods. So this FEM is built up of many small interconnected elements or subregions, which gives a piecewise approximation. That is, element-based approximation results to the problem considered. So here you can see two images. On the left side we have a cutting tool holder. Okay, a cutting tool holder and a insert. We call it as the multi-layer coated insert. That is a coating insert, for example. So these are called as throwaway inserts. Throwaway because these inserts after usage can be thrown away. And the tool holder we can use it for life. We have to replace only the tool inserts, right? So here you can see they have modeled the cutting tool holder. So that is the total domain. So that total domain is discretized or divided into finite elements, right? If I want to determine the deformation of this tool holder, then first of all I have to determine the deformation at each and every element. At each and every element I have to determine the deformation. Then by integration from the single element to the total domain, I am going to determine the deformation. So that is the basics behind the FEM. So on the right side we have a cutting tool and a rectangular workpiece which is in contact with each other. Okay, so here also you can see the type of element that is being formed. In the case of workpiece, we have triangular element. We have a triangular element. But in the case of a tool, we have tetrahedron. Sorry, we have a rectangle, that is rhombus. We have a rhombus-like shape. That is, we can have different element shapes. We can have different element shapes. The shape of the element that we are going to consider will also have an impact on the output results. So the basic idea of FEM is to determine the unknown state variables that are solved at a discrete number of points. Okay, the unknown state variables, what are they? In our machining simulation studies, the unknown state variables are my cutting force, my tool wear, my interface temperature. That are the outputs that I am going to predict, that are solved as a discrete number of points, that is at each and every element. So at each and every element, we are going to determine the state variables in the problem domain to obtain the approximate solutions. That is, for each and every element we are going to determine. Then by integrating it, we can determine the solution for the total domain. So what is meant discretization? We are continuously using this term discretization. Discretization is nothing but dividing. So the process of dividing the problem domain into an equivalent system of smaller domains. So I am going to divide the total domain into small entities, and that is called as discretization. So once a problem is discretized, the problem is nothing but a workpiece, a tool, or a beam, or a component, or a part. So once the problem or a component is discretized, the solution can be obtained for each of the smaller domains. That is, for each and every element, we are going to determine the solutions. Then, for the total domain, we are going to obtain the solution from the small domain. So finally, the domain-wise solutions, that is for the entire component or for the entire workpiece or for the entire tool, the solutions can be obtained by combining together the obtained solution from the domain-wise, that is from the element-wise. From the element, I am going to combine the solutions of all the elements so that the domain-wise solutions can be obtained. So how to combine these elemental solutions into the domain solutions? Just by integration between the lower boundary and the higher boundary, or between the lower limits and the higher limits. So the discrete points that is considered in the domains is known as nodes, and the smaller domains are called as elements. So two things that we are going to come across is the element and the nodes. So the discrete points are called as nodes, and the discretized element is known as, or small parts, individuals, is called as elements. So these elements and nodes put together, we constitute the mesh. We constitute the mesh. So node is nothing but the point, and the element is nothing but the shape of the discretized part. So the node and this element put together constitutes the mesh. If I am going to consider finer mesh size, for example, 1000 mesh size I am going to consider for a small component. Consider this as a finer mesh, that is 1000 is a finer mesh. If I am going to consider finer mesh, then obviously the accuracy of my output will be higher, but at the same time the computational time will be higher. In this case, the computational time will be higher. On contrary, if I am going to consider only 100 elements for the particular parts, that means I am going to consider coarse elements, that is bigger elements. So 1000 fine elements, 100 it becomes coarse. Obviously, results will not be that much accurate. Results will not be that much accurate, but the computational time will be lower. The computational time will be lower. So the degrees of freedom, the number of unknown parameters that each node is known as the degrees of freedom. For example, in each node I am going to determine the interface temperature, the deformation that is taking place, then the cutting force. Then the degrees of freedom will be 3. The unknown state variables at each and every node determines the, or constitutes the degrees of freedom. So in this case, if I am going to consider cutting force, deformation, interface temperature, then the degrees of freedom is going to be 3. So here you can see a beam or a simple component. So here we come across two different types of nodes. One is the primary node and the other one is the interior nodes. The primary nodes are situated at the ends and the interior nodes are positioned in the in between. So 1 and 2 are fixed and 3 and 4 I can change it to 3, 4, 5, 6. So that is how many nodes that we are going to consider. So here we come across a cantilever beam. We come across the cantilever beam. So that is represented by a model Qx is equal to Ax. Qx is equal to Ax. Now I am going to provide a force R. Now I am going to consider a force R. So for this I am going to determine the deformation that is taking place at each and every nodes. Here I am going to have 4 nodes, 1, 2, 3 and 4. The strain that is taking place, x1, x2, x3, x4. Okay, or it is nothing but the length of each node. X1 is equal to 0, the starting point, and x4 is equal to L. So that are the primary nodes, and 2 and 3 forms the interior nodes. So we can determine the deformation of this cantilever beam. Now look at this component. So this is how we are going to discretize. So this is like a dome. This is like a dome. So this dome is discretized into numerous number of triangular elements. Numerous number of triangular elements. Okay. So the reference elements is the triangular element. So each and every dot is my nodes. Each and every dot is my nodes. When it gets deformation, you can see how it has deformed. So here you can see the vertex with pink color. The vertex is with the pink color, which will get shared to the next element. The intermediate nodes won't get shared with the next element, but the nodes are the vertices. We call it as the vertices. Okay, that gets shared to the next element. Thereby the meshing is possible. So what are the different types of elements that we can have? The first one is a single point or a single node. Then we have 2 node, 3 node, n-sided polygons. So the polygons, if it is a 3, then it becomes a 3 node triangle. If it has 4, it forms a quadrangle. Then 5 means polygon. Okay. Similarly, triangle, quadrangle. Okay, look at the points. So each and every point constitutes the nodes in our study. If I am going to consider more number of nodes, obviously the complexity of the problem tends to increase. So up to 8 node triangle or quadrangle, we come with the 2-dimensional one. We consider this as a 2-dimensional elements. Coming on to tetrahedron, the 4 node tetrahedron, the 10 node tetrahedron, then 5 node pyramid, 13 node pyramid. These are all 3-dimensional elements that will be considered. During our hands-on training, we will be dealing with both the 2-dimensional as well as 3-dimensional in the afternoon session. So in that, we will clearly see how these two will be differentiated. So what actually happens, or what is the main need of going for a FEM? Apart from understanding the concept, apart from understanding the basic concepts for demonstration purposes, or how a model behaves, this can also be used for developing a new product. Okay, or a new cutting tool shape with a different shape. Okay, likewise. So conceptual design. The first I am going to have the conceptual design. Then a better model will be developed. That may be a physical, a mathematical, or a computational model. Then we are going to simulate the results. Then we are going to analyze. The outputs can be analyzed. Then I am going to design. If my design is not appropriate, once again I have to model. Then again the remodeled part has to be simulated, then analyzed. If I am satisfied with the design, then I have to go for prototyping. The prototyping is nothing but a real working model. Then the developed prototype has to be tested, and if I am satisfied with the results, then I am going to document it and then fabricate. If I am not satisfied with the test, then once again I have to go back to my initial design. So that all these things has to be changed, and again this will be repeated upon. Okay. So this is where this finite element method comes into play. If I'm going to do it in an experimental manner, then look at the amount of time that will be incorporated in that, how much amount of manpower will be wasted. With the simulation studies, this is possible, so that the computational time will be reduced by a large margin. So the computational modeling using FEM consists of 4 steps. The first one is the modeling, then meshing. The meshing is nothing but dividing the total domain into small finite elements, and then it is going to get interconnected with each other. That is called as meshing. Then I have to provide the material property. Then I have to provide the material property. Then I have to provide the boundary conditions, the initial conditions. The initial conditions is nothing but what is the cutting speed, whether it is 100 meter per minute or 200 meter per minute or 300 meter per minute, and then the loading conditions. Okay, that we have to provide. Then what are the different models that we are going to use it in machining? Okay, so 4 different models we will be using here. The first one is the lower and upper bound solutions, then shear plane model, then slip line field models, then shear zone models. So different scientists, different researchers worked on this elaborately, and they adopted their own models. So normally we will be using the shear plane models or the shear zones models. So we'll see one by one what is by lower and upper bound solutions. So the lower bound solutions employ the principle of maximum work, that is maximum dissipation of energy. Okay, because the material will be removed by pure deformation. The deformation occurs because of the applied stresses. Deformation occurs. Because of the deformation, maximum energy will be dissipated. So maximum work is done to dissipate that energy. So this system tends to reach the state of minimum energy, that is the work required to remove the material or deform the material has to be minimum. Okay, so these lower bound solutions tends to reach a state of minimum energy with equilibrium and yield conditions. So that is how this lower bound solutions work. But in the case of upper bound solutions, the strain increments we are going to consider in the plastic body. Because the workpiece is considered as a viscoplastic. If it is elastic, if I remove the load, then it will regain to its original position. So because of this deformation, a permanent deformation, or because of the application of stress, a permanent deformation occurs. With this permanent deformation, the material will tend to become plastic. So the strain increments of a fully plastic body rather than the stress equilibrium is considered in the case of upper bound solutions. So they are going to calculate the strains. So here also the principle of maximum work is employed, but rather than energy, they are using the strain. Okay, so the element exhibits maximum resistance to deformation. So initially when it comes into contact, that is when the tool comes in contact with the workpiece, initially it resists. But if the stress level gets increased out, then the deformation starts along the shear zone and the strain rates will be higher. So here the principle of maximum work is employed in the strain point of view, so that the element exhibits maximum resistance to deformation. Then comes the shear plane model. So this shear plane model is connected with the theory of Ernst and Merchant. So in the metal cutting theories, you can come across this Ernst and Merchant theory. So this is the shear plane angle phi is equal to 45 degree minus beta by 2 plus alpha by 2. Beta is the friction angle and alpha is the rack angle. So beta is the friction angle, alpha is the rack angle, and pi is the shear angle. So this theory of Ernst and Merchant provides the relationship between these three angles. So this shear plane model is purely based on Pispanian chord model. So earlier itself I told how the chip is produced. The chip is produced by this Pispanian chord model. Okay. So this is how it is. So this is like a stack of chords. Playing chords, everybody knows. Playing chords. So that is placed one over the another. So layer by layer, I am going to place chord. One chord over another chord, another chord, another chord. So now I am going to remove chord by chord. That is layer by layer. So the material will be removed layer by layer as we are going to remove chord from the set. Okay. So the chip will be straight and has infinite contact length with the two. Whether the chip will be straight? No, it tends to curve. But the assumptions that is made in this model is the chip is straight and it has infinite contact length. So shear stress along the shear plane. So you can see here. So I am moving my cursor here. So this is my shear plane, the AB. AB is my shear plane. So the shear stress along the shear plane is equal to the material flow stress in shear, because material is removed because of pure shearing action, right? So the stress is equal to the shear stress along the shear plane. Then only the material will be removed. Then the chip is assumed to be a rigid body in equilibrium. So as told previously, as we have seen, we are going to make many assumptions, right? So that the complexity of the model tends to reduce. But with the over assumptions, the model will be a lurking one that we cannot understand or we cannot expect more from the model. So the equilibrium refers to the forces on the chip tool interface and across the shear plane. The chip tool interface, what is the force that exists at the interface of the chip and the tool? Because the chip slides over the tool, so that the forces will be less or it will be the same. And across the shear plane, the plane at which the shearing action have, the forces will be in equilibrium. That is, the same force will be applied. Then comes the slip line field models. So whenever we are going to calculate this stress analysis in a plane loaded material, there are two orthogonal directions that the shear stresses are reaching the maximum. That is, the shear stresses reaches maximum at the two orthogonal directions. These directions vary from point to point. That's why two orthogonal directions. So here we come across two important things. One is slip line and the other one is the slip line field. So a line that is tangential along the length of the maximum shear. So maximum shear stress, a tangential line will be drawn and that is called as slip line. And a set of slip lines in the plastic region is called as slip line field. The set of slip lines constitute the slip line field. Or more simple, the boundary between a part that is plastically loaded and the other that not yield. So there is a line, a boundary that differentiates the material that is plastically yielded and is not yielded. So that line is known as slip line. In another means, the borders of the primary deformation zone. There are two deformation zones in metal cutting. One is primary and the other one is the secondary. The material that deforms initially is known as the primary. That deforms plastically and in contact with the cutting tool is the secondary deformation zones. So these borders of the primary deformation zone with the workpiece on one side and the chip on the other side is known as slip lines. So all these definitions are one and the same. So when coming on to the secondary deformation zone, the border between the secondary deformation zone and the chip, it is the strip line. So Lee and Schafer work. So far we have previously we have seen Ernst and Merchant. So now here having Lee and Schafer work. So Lee and Schafer work is specifically contributed towards this slip line field models. There they are given the relationship between the shear plane angle, the rack angle and the friction angle. So pi is the shear angle or shear plane angle, alpha is the rack angle of the cutting tool and beta is the friction angle. So pi by 4, pi is 180, so obviously it is 45 degree plus alpha minus beta. So this model is purely based on the slip line field models. Then comes the shear zone models. So whenever we are going to simplify things, we are going to assume some things so that we are going to move away from the accurate results. By simplified models, we are going to assume many things. So we are going to move away from the predicted results or accurate results. So this is shear zone models. Consider some features that are neglected by the previous models. So these shear zone models is specifically used in metal cutting. So in this, we are going to consider the shear stress on the shear plane is uniform. The shear plane is the plane at which the shearing action takes place. So the stress on that shear plane is uniform and no strain hardening is considered. The hardening because of the strain in the elements. And the friction angle is the friction angle, that is pi, beta. The friction angle beta. The friction along the tool chip interface, because friction takes place because of the sliding action of the chip over the tool. So friction takes place because of the sliding action of chip over the tool. So there comes the friction. So the friction coefficient mu is equal to F by N. Mu is equal to F by N. So this friction along the tool chip interface is characterized by means of constant friction coefficient mu. Right? Actually mu changes. But here in this shear zone model, we are going to consider mu as a constant because mu is equal to F by N. Since the chip moves, mu tends to change. But here we are going to consider it as a constant. So that is contrary with that of the experimental data. And also, apart from this, in the shear zone model, the effect of yield stress with the strain and strain rate and temperature were considered. Because when coming on to the models that we are going to see for flow stress, for thermal model, for friction model, tool wear models and all these things, they will be incorporating this strain rate, temperature, strain hardening also they will be incorporating that in the model. So the software has developed a model considering the strain rate, temperature, strain hardening coefficient and all these things. That's why it develops a complex model. That's why the computational times will be higher in the software packages that is used for the machining simulations. So Oxley is the person who has worked on this shear zone models. Okay, and it is found that the shear zone thickness is about 1/10 of the shear zone length. The shear zone thickness, that is the boundary. The shear zone is nothing but the boundary that is between the plastically yielded and the unyielded portion. Okay, so in the shear zone thickness is about 1/10 the thickness of the shear zone length. So a minute layer or boundary segregates between this plasticized and the unplasticized material model. So the strain rate and strain at every point in the primary deformation zone can be calculated by developing a precise model. So this only we are going to incorporate in that analytical equation or numerical equations, so that by iterations and again by iterations, okay, we are going to perfectly determine or predict the outputs. That is, at each and every point, the strain and strain rate and temperatures will be calculated in the primary deformation zone. So how we are going to calculate the strain rate? So the strain rates are being calculated based on the velocity with respect to the position of the element. Okay, and strains are calculated by integrating the strain rate with time. So strain rates are derived from the variation in velocity with respect to position, and strains are calculated from by integrating the strain rate with respect to time. Okay, so these strain rates will tend to change. The strains, strain rates, temperatures will tend to change over the time and over the iterations. So that we will see during the simulation process, how it is changing and how that will be incorporated in the model, that we can see during the hands-on training. So why we have to perform finite element simulation studies in manufacturing process? So for better understanding only we cannot use this, but also we can predict some outputs before going for an experimental setup. For an experimental setup, in order to reduce the time, the cost associated with the experimental machining process. So the purpose is to validate the results. We are obtaining a results, whether it is perfect or not, that can also be simulated, and that will be approximately nearby. So to determine the performance of and the effectiveness of the system. The second one is to determine the performance and effectiveness of the system. We are going with the FEM. To determine the optimum conditions. So for this material, if I'm going to machine it with particular tool, what should be the cutting speed, what should be the feed rate, what should be the depth of cut, that we have to use, so that my tool wear should be less, lower cutting forces will be developed, and low interface temperature will be achieved. So that combinations, that optimizations can also be done by this process. And finally, in the economic aspect, so we can reduce the production time and the cost associated with the final product, because we are not going to do many experimental works. We are going to simulate it, and finally we are going to validate with the experiment. So the various manufacturing processes that can be modeled and simulated are the turning process, drilling, milling, forming, rolling, and friction stir welding. Also nowadays it is being simulated by using many softwares. So what are the general considerations in modeling and simulating of machining process? So what we should generally consider in these things? So first thing is to discretize the total domain to describe the physical behavior of a process. So first one is to discretize. So these finite element simulation studies is mainly used because of its ability to describe the arbitrary shapes and field variable distributions. So to describe the arbitrary shapes, so whatever shape that we can select, for example, consider a forming. I am going to study a forming process. I can shape any component. For this, I have to design a die. So arbitrary shapes we can select, and also field variable distributions, right? So that can also be calculated. the die stress, the stress that is acting on the die, the cutting forces, the deformation that is taking place, the temperature that is associated with that, what is the wear on the die. So these are the field variables. So how this is being distributed and changed, that can also be studied by this. But the problem that is associated with the discretization is the extreme range of length scales that we will be using. The length scales that we will be using in the study. So here we will be coming across two different types of length scales. Okay. So in the case of surface microstructure, we have to come across sub-millimeter scale. You know, whenever I am going to see the surface of a machined component, I have to go with optical microscope or I have to use the scanning electron microscope. So magnification I have to do. So 100 microns magnifications. So that comes under the sub-millimeter scale phenomena, right? But residual stresses, the temperatures and all these things comes under the meter scale product. Temperature, degree centigrade, then Newton per millimeter square, Newton, the pressure is in Newton. So similarly like that. So there are two different types of length scales that is involved in this, right? So the current modeling and simulation does not permit the concomitant simulation, that is parallel simulation of small scale effects over the entirely of a large product. So that has to be simulated separately and this has to be simulated separately. So simultaneous simulation is not possible at this present conditions. That is, we cannot study the microstructure and at the same time we cannot study this also, that is cutting force measurements, interface temperatures, that we cannot include now. So that can be studied separately. But researchers are working on that so that in the near futures they can have both this integrated into a single package. So based on this, the length scales that is involved in machining process is grouped into two categories. The first one is large scale models and the second one is small scale models. Small scale and large scales. So large scales capture overall part and machine tool behavior, whereas small scale model focuses on interaction of cutting tool and workpiece in localized regions. What is the strain rate that is happening in each and every element. So that becomes small scales. What is the deformation of each and every element? That is a small scale. Overall part, that becomes the large scale models. So the examples for large scale models are numerical control toolpath, NC, we call it as NC, numerical control toolpath, checking the final shape of the part, so the interference between the cutting tool and workpiece, so calculating the MRR and all these things and volume calculations, that we are going to make it in the large scale models. So NC toolpath, the shape, the interference that exists between the cutting tool and workpiece, then volume calculations, material removal rate, MRF stands for material removal rate calculations, and all these things that will be carried out in the large scale models. So most of the basic models does not include analytical equations, but they include only volume and geometrical interactions. The basic models interact with volume as well as geometrical interactions. But more sophisticated models rely on mathematical equations, that is the analytical equations. So the simplified versions uses volume and geometrical interactions, but the more sophisticated, that is complex models, uses analytical equations. But in the case of final simulations, we will be using partial differential equations. So the Vericut software that is used by CG Tech, so it is a verification program that includes optimization functions that is based on geometric chip load calculations. So what is the load, and for this what is the chip? So that can be calculated by this Vericut. Then comes the another package that we will normally using for the finite element simulation studies of machining process, the Advantage. Okay, that is developed by third wave systems. So this uses finite element based power calculations to optimize feeds and speeds, that is the cutting speed and feed rates. So by using the software advantage, we can do milling operations, we can do turning operations, and we can do drilling operations. So the dissociation of each and every element, because the total domain will be divided into finite elements. The dissociation of that element. Okay, why the dissociation takes place? Because of the residual stresses. Because we are going to have a shearing action. Because of the shearing action, some residual stresses will be there in the material, that is in the individual element. Okay, so by using this, we can study the cutting forces that is induced by this process. So distortion due to relief of prior residual stresses and cutting forces that is induced can also be studied by these models. So the earliest and simple models, so as told, it is purely based on volume and geometrical interactions. Okay, and apart from this, the earliest models apply empirical observations. The empirical observations is nothing but developing a model using experimental outputs. Developing a model using experimental outputs. Based on that, we are going to derive some relationship between the force, velocity, power. So by equating this, we can predict the cutting forces. That is, a model will be developed by means of regression analysis based on some experiment. So in that, I am going to substitute some input values so that I can predict the cutting force. In analytical chip forming models, the analytical is the mathematical model, the partial derivation equations that we will be using is applied, that applies plasticity theory. Okay, because the metal will be sheared so that it becomes plastic in nature, then only it will removed as chip. So that apply plasticity theory to characterize the interaction between the tool-edge workpiece and chip. So there are three interfaces, we call it as the interfaces. Tool and the chip, that is the first one. Tool and the workpiece, then chip and the workpiece. So these are all the interfaces. So by using this plasticity theory, we are going to form the chip formation models. So Ernst and Merchant, okay, first applied this plasticity theory to predict the cutting forces. Okay, in the year 1938 itself. So they uses the shear plane model. So earlier itself we have seen that Ernst and Merchant, theory of Ernst and Merchant uses the shear plane model. Okay, so shearing occurs along the shear plane and the shear stress on the plane is equal to the shear yield stress. So this statement we have seen in the shear plane model itself. That is what the work of Ernst and Merchant is. So by using this, that is shear stress is equal to the shear yield stress in the shear plane, a force balance was derived, cutting and thrust forces were predicted. So based on these assumptions, we are going to predict the cutting forces. So the finite element models that incorporates this plasticity theory will be an alternate to the finite element models that uses analytical models. So finite element simulation studies by developing a model based on plasticity theory will be far better than that of the analytical models. So they can also predict three-dimensional chip geometry. Nowadays we are moving from two-dimensional to three-dimensional. We are moving from two-dimensional to three-dimensional so that we can clearly see the geometry of chip, the chip morphology we call it as, the cutting forces, the temperatures, changes in the tool, workpiece and chip, each and everything we can visualize by means of this plasticity theory. So the models use solid models of actual tool geometry rather than simplified shapes. So we are not going to use any simplified models or simplified shapes or components. We are going to use the realistic shape, how a cutting tool will be, how a cutting insert will be, what will be the shape of the workpiece. That only we are going to use. That is, we are going to use only the realistic model, that is realistic solid models. So this is the exact scenario of the turning process. We have a tool, we have a chip that is being produced, we have the workpiece. The tool will come into contact and the chip will be getting removed from the workpiece along the shear plane. Along the shear plane. So along the shear plane, the shearing action takes place. So the material will become plastic. Will come to the plastic state and it is being removed. So here you can see the material of the chip. The chip slides over the cutting tool. There comes the friction. There comes the friction models. The flow of material is described by the material flow model. By the material flow model. The temperature that prevails in between these interfaces will be determined by the temperature model. So for each and every entity, we are going to develop a model and put together all these models. We call it as a software package. So categories of finite element models. There are two categories. One is steady state and the other one is the transient. The transient changes with respect to time and the steady state won't change with time. So once we have to determine the outputs, only when a steady state is obtained. Only when a steady state is obtained. In the transient conditions, we cannot, whatever things that we predict is only a wrong. So we have to predict things once a steady state is obtained. So the steady state models represents a snapshot in time. An assumed chip shape is used. So we'll see this what we are going to do during the hands-on training. So what this assumed chip shape, because we have to remove some chip with that of the environment. So a chip shape that we are going to produce, that is a steady state is reached. So the shape may be modified in order to determine the solution. That is, a part of the chip will be removed so that a chip shape we are going to assume. But contrary to this, the transient models track the evolution of chip geometry in time. Over a period of time, how the chip will be produced and what is the shape of the chip, that will be determined by the transient models. So the tool entry, where the tool comes in contact and where it exits, how the chip flows, what is the shape of the chip, and how much it makes contact with the tool, each and everything we are going to model in these transient models. So each and every model, that is the steady state as well as the transient models, have its own advantages as well as disadvantages. In the transient models, it includes the steady state chip behavior because the chip will be removed from the workpiece. Okay, the chip will be removed from the workpiece, then it comes in contact with the tool, there will be friction, then it tends to curls out. Okay, so the unsteady chip behavior is found. So these models that we are going to use require special treatment, okay, for chip separation through predefined separation surface or through frequent remeshing. Okay, so this frequent remeshing, we call it as adaptive remeshing. In the subsequent slides we will see that adaptive remeshing, what is that? Okay, so after the chip is separated out, the adaptive remeshing automatically remeshes so that it manages the severe deformation that occurs at the tool edge. So calculation times can also be significant, right? And reaching the steady state tool temperatures is not practical without special treatment. Okay, we cannot predict or we cannot consider the temperatures in the transit zone because it tends to change with respect to time. So for this purpose only, we have to do some special treatment, that is eliminating a part of the chip from the produced chip. A part of the chip will be removed. Then again we have to simulate, thereby we have to reach the steady state condition. We have to reach the steady state conditions, and then only we have to measure the outputs. Then comes the steady state models. So these models, once a steady state is reached, there is no more change. Once a steady state is reached, there is no more change in the temperature or the chip morphology. So in that condition only, we have to capture the temperature and the chip behavior, whether it is segmented, whether it is continuous, whether it is discontinued, whether it is with the built-up edges. That and all these things we have to calculate or determine only when it reaches the steady state model. So during this steady state models, remeshing is not required. But in the case of a transient model, remeshing is required. For that only we are going with adaptive meshing. But once the steady state models, no remeshing is required because the distortions will be less. Once the steady state is reached, the distortion level will be very, very less. So we are going to just ignore that. So no special treatment is required because the position of the tool does not change. So no special treatment is required. That is eliminating a part of the chip from the produced chip. Then we come on to the 2D versus 3D models. So two-dimensionals. So for orthogonal cutting simulations, two-dimensional models are more appropriate because it considers only little computational time. It takes only little computational times. So compared to the three-dimensional models, these two-dimensional models are significantly have a shorter calculation time or computational time. So a drastic reduction in computational time is there. But with these two-dimensional models, we can know exactly or we can determine how a process behaves. We can interpret some knowledge or some outputs from the simulation studies. So surface residual stresses we can determine. So physical behavior of tool, the physical behavior of workpiece, and all these things we can calculate from these two-dimensional models. So these two-dimensional models are appropriate for applications that require greater deal of resolutions, such as surface residual stress or microstructure areas that we are going to study. But when compared with the 2D model, we have to prefer only 3D models. Then only the chip morphologies and all these things we can clearly see. But we have to accept the larger computational time that these models takes place. So these 3D models are appropriate for studying the geometrical details of actual cutting tools. Okay, so that cannot be actually represented by the 2D models, the chip morphology, how it is going to take place. Okay, so we will see that in this hands-on training also. We will be doing both in 2D as well as 3D. But with the same dimensions, compared with the 2D, this 3D have larger computational times. Okay, it has larger computational times. Even it will run for a day or a two, depending upon the finer meshes that we are going to consider. Okay, so I have simulated this machining process, and it takes place over 10 to 12 hours also, that I have carried out also. But these 2D models, it will provide results within an hour, within half an hour or 1 hour, we'll get the results. So when there is any practical limitations in times, so we have to stop with the 2D models also. But if I want to study in depth the chip morphologies and all these things, it is better to go with 3D models. So what are the historical developments in this machining simulations? So in which year we have started, the researchers who have contributed to the development of models, who has used which models, that and all we'll see in this content. So because of the growing industrial needs, these finite element simulations come into exist in late 1980s, and its development continues towards 1990s until 2000. Okay, it started in the late 1980s, and for a decade it has continued its growth. So it started in the year 1985 when Stenkovsky and Karol described a finite element model. So they have used orthogonal metal cutting and uses Lagrangian approach for analysis. So they have considered orthogonal model and they have used Lagrangian model. We will see what are the different models. Arbitrary model is there, Lagrangian model is there, arbitrary Lagrangian model is also there. That we will see later on. Okay. Then in the mid 1990s, right? Apart from the Lagrangian approach, scientists and researchers has also included automated remeshing techniques. So before, at each and every iterations, we have to manually remesh. We have to manually remesh and then we have to simulate. But automating remeshing provides better results. So when combined with the Lagrangian simulations, it produces better results. And in the year 1992, Chacon and Chenot, so once again simulated the orthogonal cutting with automated remeshing using 42 codes. Right? So two models in the previous slide itself we have seen orthogonal cutting process with the shear zone model, which is under criticism. But we are not going to model any oblique cutting. So oblique cutting is the real time in experimental studies. So that's the problem. So by considering orthogonal machining process with the shear zone model is still under criticism. Then in the year 1993, Kamako, Maurice and Ortiz introduced a continuous remeshing techniques that is used for high-speed machining. So Lagrangian approach and then the type of machine that they are considered. Then in the year 1996, the first package of deformed 2D was introduced in which the remeshing was adaptive. The remeshing was adaptive in nature. Okay. Then in the year 1997, they have used Eulerian simulation. Stenkovsky and Atvale used Eulerian simulation, so that is suitable for simulating tools with chip control. So what type of chip that we are going to produce? So until 1997, most of the simulation studies are focused towards 2D studies, 2D simulation only. But in the year 2000, Corrective modeled the first three-dimensional threading process, okay, with automated remeshing. So he only developed the first automated remeshing three-dimensional model for simulating the machining process. So it is the year 2000 we first received the 3D models. So why we are going to consider turning? So see here we are going to consider only the simple example of machining, that is turning. So normally metal cutting problems are non-linear and dynamic. They are non-linear, we cannot predict, and it is dynamic. It changes with respect to time you cannot predict parameters because it mainly depends upon the friction coefficient that exists between the chip and the cutting tool, the action of the cutting fluid. So previously itself I have told cryogenic is different, flood cooling is different, dry cooling is different, and the MQL is different. So what is the action of cutting fluid that we will be using, and the property of the material, So this makes it a complex thing, complex product. So when comparing with that of the 2D, the 3D, with the 3D the complexity increases, but accurate results can be predicted. Even though we call it as accurate, it is only an approximated results. So we have to be very, very careful. Even though it is accurate, it is only an approximate results. But at the same time, higher computational time is used. When comparing with the 2D, these 3D models provide a detailed information of stress and strains and the interface's temperature, the type of chip produced, and all these things. So better go with 3D models than that of the 2D, so that the perfect information on stress, strains, the interface temperature, the shape of the chip that is produced can be determined. So in machining process, normally we come across three important analyses. First one is the Eulerian theory, the second one is the Lagrangian theory, and third one is the arbitrary Lagrangian and Eulerian theory, ALE analysis. We call it as the ALE analysis. You can Google it and you can find n number of papers on this. So what is Eulerian approach? So in this, the element is spatially fixed. So the material flow to simulate the chip formation. For chip formation, the material flows through the element. The material flow through the element, and it forms the shape of the chip, shear angle, and the contact conditions. Okay. So here an iterative procedure is used. That is iteration. 100 iterations, 200 iterations. Okay. If I'm going to stop with the 10 iterations, then the chip will not be seen. If I go with 1,000 iterations, then a clear chip can be seen. So use higher number of iterations. So if I'm going with 1,000 iterations on all these things, then it will take 2 days to complete the simulation studies. So in the Eulerian approach, the element mesh is spatially fixed, covering a entire volume. So the element sites that are the boundaries of the chip. The element sites are nothing but the boundaries of the chip. Okay, that are adjacent to the rack face of the cutting tool. That is adjacent to the rack face of the cutting tool, or repositioned to be tangential to the cutting position. So the element sites that are on the adjacent sides of the rack face, right, are repositioned to the tangential to the cutting position. So that is the meshing that it is going to take place. In the case of Lagrangian approach, the elements are attached to the material. In the previous condition Eulerian, the elements are spatially fixed, but here the elements are attached to the material. So that is the advantage of Eulerian and Lagrangian approach. So the deformation of the material is because of the shearing action of the cutting tool. Okay. So the deformation of the material takes place because of the shearing action of the cutting tool, so that the chip will be formed. So the unconstrained material flow. The unconstrained material flow in Lagrangian formulation allows the simulation from incipient chip formation to, that is, transient conditions to steady state conditions. Okay. So in Lagrangian formations, you can move from transient to steady state conditions. So that is also an advantage of this Lagrangian approach. So apart from this, we have also take care of the strain rates, temperatures. Okay, apart from this, the models that we are going to use in Lagrangian approach mainly depends on the strain rate, and temperature. Okay, that is applied to the workpiece. So I am going to consider a workpiece. So the behavior of the workpiece will be dealt by means of the strain rate and the temperatures and all those things. Now we are going to combine this both Eulerian and Lagrangian approach. Okay, so it combines the advantage of the two. So in the case of Eulerian, the element is spatially fixed with respect to the volume. And in the second case, the Lagrangian, the element is fixed to the material. So here in this case, in the ALG, arbitrary Lagrangian Eulerian approach, the mesh is neither fixed nor attached to the material. So it moves arbitrarily. So randomly it moves relative to the material. So the total displacement of the material, consider an element. So what is the displacement of that element? How to decide? So the total displacement of the element is nothing but the Lagrangian displacement plus Eulerian displacement. That gives the total displacement of the element. So the Lagrangian step is used for the material flow at free boundaries. So where we are going to combine this? So for material flow at free boundaries, we are going to use Eulerian, and the chip formation is a result of material deformation. So that is also Lagrangian. Then in the Eulerian step, the reposition of the element takes place. So previous itself we can see here in the Eulerian, that is fourth point, you can see the reposition to be tangential. The element sides are repositioned to be tangential to the cutting position. That we are going to use it here. So in the Eulerian step, the reference system is suitably repositioned to compensate for the distortions. Okay, so in the previously we are going to consider the Lagrangian step. Okay, which considers the material flow at the free boundaries and chip formation because of the material deformation. Here, in the case of Eulerian, we are going to reposition the reference system of the element due to the distortions taking place. So this procedure involves some small time increments. So this procedure involves some small time increments, and it does not alter the elements or the interconnectivity of the mesh. So by involving this ALE approach, the elements will not get altered out. The elements will not get altered out, and the interconnectivity of the meshes won't get disturbed. That is the most important advantage of going with ALE. Okay. So what type of approach that we have to use? That can also be selected in the simulation software. So additionally, no separation criteria or extensive remeshing is required because we are going to consider only adaptive remeshing. So no separate criteria is required for this approach. So because of this, when compared to that of Eulerian or Lagrangian, this ALE mesh is less distorted because it moves arbitrarily. That's why it gets less distorted. Okay. Meshing. What does this meshing means? So how we are going to interconnect? How we are going to divide the total domain into finite elements, and how these finite elements are interconnected with each other? That is the meshing. Whether we are going with the coarse element or small or fine elements. Initially we are going to decide, and then how we are going to interconnect. That decides the computational time and also the accuracy of our results. So the initial mesh is very significant. Okay. So the convergence of the numerical procedure and the accuracy depends mainly on the mesh that we are going to have, and that obviously depends on the size of the element. So the element, the mesh, we call it as the element also. So the coarser mesh is used for testing a model. So I am going to initially test a model. The output I cannot rely upon. So if I want to test, then I will go with a coarser model. And a final model is required when I am going to check a model. So testing and checking. Testing, just how it is, what type of chip is produced, that we can decide by using a coarse mesh. The finer mesh, if I want to check how a system behaves, how we are turning processes, then I have to go with finer meshing. So accuracy level will be higher in finer mesh and higher computational time in finer mesh. So another technique is to identify the regions that are of more interest for the analysis. So in a turning process, the region of interest is the interfaces, where the cutting tool comes in contact with the workpiece. So in that cases, we will have finer meshes, and away from that interfaces, we can have coarser meshes, so that the computational time will be reduced. So I am not going to consider finer meshes for total workpiece or for total tool. Only at the interfaces I am going to consider finer meshing, and away from that I will be going with coarser meshing. So these finer meshes can also be used in these regions that are combined with the larger ones in other regions. So that's why I told at the interfaces we will be having finer, and away from that interfaces we can have the coarser that can be merged with each other. So two deformation zones have to be particularly important in machining process. One is the primary and the other one is the secondary. So in these zones, we should have a dense meshing, that is finer meshing should be there, because there only we are going to determine the cutting forces, the interface temperature, the pressure, the stresses, all these things, right? Then strain rate, temperatures, everything we are going to determine only at the two deformation zones. So at the two deformation zones, the meshing should be denser or finer. If I am going to consider a coarse mesh at that point, then I cannot rely upon my results. So this is, so here I am moving my cursor now, the primary deformation zone, that is where the shearing action takes place, and then we can see the point of contact of the material with the cutting tools. So in the primary deformation zone, you can see how dense my meshing is. If I move away from this primary and secondary deformation zones, we can see a coarser grain or coarser meshes. You can see here. So this is a two-dimensional. So here we are going with a triangular element. So on the right side also you can see. So at the place of contact we can see finer meshes, and when we move away from that you can see a coarse meshes. So this will be taken care by the system itself. Then boundary conditions. What are the boundary conditions? So which part to move and which part to be stationary, that we are going to decide. Okay, some researchers will be using the movement of the cutting tool, and some researchers will be using the movement of the workpiece. So if I am going to apply a boundary condition to the workpiece, then the cutting tool has to move. Okay, that on all things we will see during the simulation studies. So boundary conditions is either the workpiece will move or the cutting tool will move. Okay, while the tool moves, obviously the workpiece will be constrained, so it will not move. If the workpiece is moving, then obviously the cutting tool will be constrained. In material models, so how the material is going to flow, because based on the material model only, the material will shear upon and then it will flow as a chip, right? So there are many constituent equations that describe the flow stress or instantaneous yield strength. Okay, so based on this, the material has to deform plastically, then only it will be removed as chip. So there are elastic deformation and plastic deformation. Once the condition of plastic deformation reaches, then only the material will be removed as chip. So these elastic strains are much more than that of the plastic strains. So plastically it has to strain and then it has to get out as the chip. So what are the different constitutive models that is present or used in literatures? So elastic plastic, then elastic viscoplastic. So what is the viscoplastic? So these viscoplastics are time dependent, that are irreversible, that has irreversible strains. So plastic means once we remove the load, it will not go back to its original position. The viscoplastic is, it is time dependent and it is also irreversible in nature. Then we have rigid. Rigid means no deformation. In elastic, there will be deformation, but when I remove the load, it will come back to its original position. But in the case of rigid, zero deformation. We call it as zero deformation. Then we have rigid viscoplastics. So what are the strains and temperatures in the two deformation zones? So we will be considering the primary and secondary. In the primary deformation zone, the temperature will be around 150 to 250 degrees centigrade. But in the case of secondary deformation zones, higher temperatures in the order of 800 to 1200 degrees centigrade will be there. Okay, so that much amount of heat has to be dissipated out. That's why we will be using different types of cutting fluids. So these are the different material models that we will be using. Uzi tool wear models, then Oxley tool wear models. So these are the names of the researchers who have developed these models. So they have the constant K, temperature T, then B is another constant, epsilon dot is the strain rate. Okay, so epsilon is the strain and N is the strain hardening. So C is a material constant, likewise. So different material models that are developed by different researchers, Uzi, Oxley, Johnson, Cook. Okay, the first three will be generally used. Then comes the flow stress measurements. So what is the flow stress? It is the stress required for the increment of plastic deformation of a material for a given strain. So the stress required for increment for the plastic deformation state. Then only it will be removed as a chip. Otherwise, it won't get removed. So for a given strain rate and temperature. That's why in these models you can see it is the temperature, strain rate, and also the material properties we will be getting added upon. So this also includes the material properties like a grain, the phase, whether it is the eutectic phase, periodic phase, and hardness of the materials. So these and all these things we can also see during the hands-on training session. So how to determine this flow stress? So this flow stress measurement is very, very essential when I develop a new material. If I want to define a new material in the software package, then I should know the flow stress measurement. For example, I have developed a composite material. For example, aluminum metal matrix composite. Now I want to do turning simulation studies. So how to define this new material into this package? So it has some constant materials. ASA 1045, ASA 1020, then titanium, then stainless steel it has, many aluminum it has. Okay, but how we are going to incorporate this composites? For this, we have to determine this flow stress measurement. How? We have to do a tension test in the universal testing machine, UTM, or compression or shearing. And then we have to include the data in the software package so that a new material can be determined. But there is also some problem in that, because the strain rates in machining exist 10 to the minus power per second to 10 to the power minus 6 per second. So high strain rates. So in the initial slides itself, we have seen in small regions at the high speeds, higher strains occurs. In small regions, higher stress and strains occurs. But in the case of tensile and compression test, the strain rates will be under 10 to the power 2 per second. So a exact amount of material, a exact amount of strains cannot be included into a study. So for this, initially we have to do some experiments on turning. If I am going to do some experiments on a turning for the composite material, and that data should be included in the packages. That data should be included in the packages, and then we can define a new material. So even for high-speed compression test, the results will be only lower than that of the machining studies. So that's why with this flow stress measurement using compression test or tensile stress, we cannot provide as accurate model, a material model into the. So for this purpose, we should experimentally, practically we have to do some experiments in turning, and based upon that, the material model has to be developed. So this Johnson-Cook model, JC, we call it as the JC equation. So a Johnson-Cook model suggests the flow stress as a function of strain, strain rate, and temperature. So if I am going to consider this JC equation, obviously the flow stress will be a function of strain, strain rate, and temperature. So in the package itself, some standard materials are there. For study purpose, we can directly use them. So in Johnson-Cook model, we will be using this equation. The flow stress sigma bar is equal to A plus B eta power n. What is A? A is the basic strain, that is a hardness, and beta and n are the strain hardening behavior coefficients, and C is the sensitivity, and M is the thermal softening behavior. So strain, strain rate, temperature, everything we have to include in that. The friction model. The friction is particularly available in the secondary deformation zone. It is where the chip contacts the tool. So primary deformation zone is between workpiece and chip, and secondary deformation is between tool and the chip and tool and workpiece. Okay, it is the interface. So it is important to determine the cutting force, but also tool wear and surface quantity and quality. So it all depends on the friction models that we will be using, and the friction model that we will be using in the standard packages are the Coulomb law, that is mu is equal to F by N. Mu is equal to F by N. So initially itself we have seen that the friction coefficient is constant. We have considered, or we have assumed, that friction coefficient mu is constant. But normally in experimental turning process, the friction coefficient will not be constant, but we have to assume it as constant. So these are the various models that we will be using. So Coulomb friction, Zorov, then Uzi model, Chills model, Iwata model, Chekron and Chenot. So similarly like, but normally we will be using this Coulomb model for friction models. Then comes the main thing, the adaptive meshing. So here you can see a simulation. Here the workpiece is stationary. So the boundary condition is, I am going to put the workpiece as constraint, so it will not move. The cutting tool insert is moving and it is removing the material. So what is, you can see there at the contact point of a tool with the cutting force. There you can see some meshing take place adaptively. You can see that the meshing is automatic there, and that is called as adaptive meshing. So it is a remeshing techniques. So the disordered element mesh will be replaced with a new one. Okay, because of the stress, the elemental mesh will be disordered, and in this adaptive mesh, that mesh, the disordered element mesh will be replaced with a new mesh. There you can see in the simulation also, it is getting meshed up. So this refinement technique increases the density of the mesh, okay, by smoothing process. So that accurate results can be predicted by this adaptive meshing process. So this adaptive meshing increases the accuracy of the simulation, but the computational time will be higher. So here also you can see during at the contact point, you can see dense meshes can be seen. So here you can see it is larger one, but as this tool progresses, here it becomes denser. The coarse meshes will tend to become fine meshes. So this is what you are going to study in this deform 3D packages or 2D packages. So here this is my workpiece which is going to rotate, and this is the throwaway inserts called as cutting inserts. So here we are going to get interest only on this part. So this blue color is my workpiece and this yellow is my cutting tool. So this is just a model of that. So this is the workpiece and this is the cutting tool, and as the cutting tool moves, chip will be removed. That is, it is found that in this case the tool is constant and the workpiece is rotating, so that it moves here in this direction. The cutting tool, the workpiece moves or rotates in this direction. And this is for two-dimensional one. So this is the 3D and this is for 2 dimension. So what are the different chip formation models that we will be having? So chip formation models is chip separation criteria. So damage criteria or wedge indentation process. So in the damage criteria we have physical and geometrical, the element deletion technique, the node splitting technique, then remapping, and all these things will be having. So these are the different types of chips that can be normally produced. So continuous chips, the discontinuous chips, the segmented chips, and the laminar chips, and also built-up chips can also be produced. So this is the ALE formation, arbitrary Lagrangian Eulerian formulations. This is how the chip is going to flow, and this is the workpiece, and this is the movement of the here the tool is kept constant and the workpiece is moving out. So here we come across two important terms. One is explicit and the other one is the implicit. So what is this explicit and what is that implicit? Explicit is nothing but, so we will use some words like that. Explicitly I am telling you. Explicitly, that is clearly I am telling you. So something, if I am going to state something clearly and plainly, that is as it is, then it is a explicit one. And in the case of implicit, it is not stated directly. So indirectly I am going to determine things, and that's the difference between explicit and implicit. So in case of explicit study, so at each increment the values of field variables and the derivatives are at the previous increment. The values determined from the previous increment. But in the case of implicit, we are going to determine the values based on the previous and the current increment. So we have to consider the previous increments also. So in explicit, we require larger number of small time steps, right? But here in the case of small number of larger time steps, we are going to consider in the case of implicit. And in the explicit, it is conditionally stable, and in the case of implicit, it is unconditionally stable. So here in the case of explicit, we are going to determine the solution at the end of each iteration, each increment without iterations. But here we have to perform iterations until a convergence is obtained. We have to perform iterations until a convergence is obtained. So we have to iterate things. So this is the thermal models. So you can see where it is plastic works and friction. So friction can be seen on the cutting tool sides. So where the cutting tool, that is cutting tool and workpiece, cutting tool and chip, that is the interfaces. And plastic work is between the tool and the workpiece and also the chip on the workpiece. So this is where the heat dissipation occurs. The heat transfer that exists between the workpiece and the atmosphere, that is represented by the red colored lines with the environment. So because it is in direct contact, but the interface temperature that is represented by yellow color lines are the interfaces that exist between the workpiece, cutting tool and chip. So it becomes the conduction. By the elements it has to conduct. So there only we are going to supply the cutting fluids so that the heat will be dissipated out. So here we are going to come across some examples. So I am nearing my presentation. The first one is the 2D simulation of turning process. So here in this study I am going to consider 3 different cutting tool inserts of different shapes: C shape, D shape and S shape. That is the angle included. In the case of C shape, the included angle, that is this is the included angle is 85 and here this is 55. The angle is 55 and here it is 90. In the S shape it is 90 degrees. So accordingly I have designed the cutting tool and workpiece, and this is the place you can see denser meshing. This is where the cutting tool will come in contact with the workpiece, and here this is the boundary condition. Here the workpiece is fixed. Okay, so similarly many cutting tools I am going to develop, and then I am going to simulate the results. Here you can see these are all coarser grains. As I move towards the interfaces, you can see finer grains, and this is a continuous chip. You can see a continuous chip is being produced, and the temperature is around 940 degrees centigrade. We are having at the interface temperature. So this is the maximum principal stresses. The maximum principal stresses are on the primary deformation zone. And this is how the cutting forces. This is the cutting force. It is exactly at the point of contact of cutting tool with the workpiece. Here you can see the cutting forces are acting. Then we come across the 3D simulation of turning process. So here these tools were modeled using SolidWorks. For 3 different inserts: C shape, that is 85 degree, and D 55 degree, and S 90 degree for different relief angle and nose radius. And then we are going to simulate these studies, and at the same time we are going to predict the interface temperatures and all these things. The cutting forces you can see here. Similarly for 18 tools we can see, and also we can, in the previous slides itself we can see what is the influence of any input parameters that can also be studied. So here I am going to consider 3 different cutting speeds: 227 meter per minute, 256 meter per minute, 285 meter per minute. And what is the change in temperature? Here you can see more or less this 256 and 285 produces a similar set of temperatures, that is around 940 something. Similarly on the mean stress, so more or less all these things are going to produce the same type of stresses. So with this I come to the conclusion of today's session, morning session. If you have any doubts, you can come to the chat session. You can ask your questions and I will answer your queries so that it will get clarified out. And be exactly at 2 o'clock. For hands-on training session. So first thing that I will be doing in the hands-on session is 2-dimensional machining simulation. And after that we will be going with 3-dimensional simulation using Deform 3D software. Okay, I stop this presentation now, and thank you.